All right. So, let me see. Check out my Eclipse t-shirt from Oregon 2017. It's an amazing thing. If you ever get a chance to see an eclipse, you should do that. I think the next one in the US is in 2024. So get ready. At any rate, I want to talk a little bit about the Unit 1 project. So let's have a look at that packet. Come on. Because I think part of it, it's just hard to get started on it if you don't know where to begin. So what I'm going to do is go to the front page. I'm going to zoom out a little bit so we can see more of it at one time. And now I'm going to jump past the fractals. That was just kind of for fun. To the actual work we need to start doing is right here, right? So the first thing you're going to do is watch this little video, and it's so short, and really the only thing it shows is a guy dropping a ball, and they use a strobe light. Whoops. They use a strobe light, kind of like these fractals are strobing on us. They use a strobe light to capture the location of the ball while it's falling. So don't think of this as 10 different drops of the ball. This is one drop of the ball and a super fast camera that was able to catch the ball in midair in these 10 different locations as it fell towards the ground. It was being accelerated by gravity. That's the A of F equals ma, right? The mass would have been how heavy the ball is itself. And the force is shown by its movement. So we've got this little event where we're looking at this falling ball. And the first question that they want you to do is list information that you think we should collect in order to study how fast this ball is falling. What a thing to study, how fast a ball is falling. It's so common. It's such an everyday event. Well, this, I think, goes to show that in science, you can study anything, whether it's very common or whether it's very unusual. We can get information from it and apply it to our own lives. So, what kind of information should we collect if we want to study? Notice, what are we trying to study? It says right there, we want to study how fast it's moving, right? So what does that involve? If we're going to study how fast something is, that's its speed, right? So would that be something we'd want to study? Is that some information we should write down? Is it speed? So maybe you'd add that on there. But wait a minute, what is speed really? It's a distance in a certain time. So when we say something's fast, we're not only talking about how far it went, we're also talking about the time it took to get there. So if we're going to study something that's moving and study its speed, how fast it is, don't we need to know something about the time that has gone by and the distance that it has moved? So on this board on the background, we can see the different distances that the ball has fallen. Here at the last one, it has fallen 3 meters at position number 10. Or maybe you want to call this image number 10. I kind of prefer position 10, but on your paper it's calling it image 10. At any rate, we need to know its distance. How far has it gone? That's something else we should collect information about. Well, wait a minute. That wasn't all of speed. Speed also included the time it took to cover that distance. How long did it take to fall 3 meters? Well, that's what this number is telling us right here. The time that's going by. I know this is a complicated number to work with, but don't worry about that. But don't we need to record the time? Isn't this another piece of information that we should list up here? Let's think about some other possibilities, and these might or might not be relevant to what we're studying. For example, do we need to record the color of the ball? Does that seem relevant to learning about how fast it's falling and how gravity is acting on it? Does the color really matter? If not, we wouldn't need to write it down. What about the size of the ball, or the mass of the ball, or the shape of the ball? Would any of these really influence how fast it's falling? I want you to think about those things. What about the more proper term for speed, you might remember, is velocity. Is that something we might want to record? And then, oh yeah, velocity, there was something else that was called a change in velocity. If the velocity is changing, then we call that acceleration. Is that something we might want to record? So, for example, look at the space between number 4 and number 5. And you see how that is a smaller space than the space between number 9 and 10? Doesn't that mean that the ball is falling faster over here than it was earlier? In other words, it is accelerating. And that's because of gravity. It accelerates. It falls faster and faster because each of these numbers is the same amount of time apart. But you can tell that the distance that the ball falls during that time is less. The actual time between each of these numbers is right over here, 0.0087 seconds. But let's just pretend for a second that it's only 1 second apart. So to begin with, at position 1, he's just at this very moment let go of it. It hasn't moved at all and no time has passed. It's at 0 seconds. Now let's pretend that every number is 1 second and it actually took 10 seconds to fall this far. We know it didn't. It fell much faster than that. But wouldn't that mean that position 2 is 1 second after position 1? Position 3 is 1 second after position 2. Position 4, 1 more second has gone by. Another second, another second. Every number means another second has gone by, except it's not really that a second has gone by. It is that 0.08 seconds have gone by. A tiny fraction of a second has gone by, but they're all evenly spaced amounts of time. And that's because the strobe light that's flashing is flashing at this speed. It flashes every 0.087 seconds. And by flashing right then and taking a quick photo right then, we can capture the position of the ball as it's falling 10 times before it even hit the ground. It didn't fall very far, and yet we got 10 photos of it that were each 0.0087 seconds apart. Okay? So right here, they want us to start collecting some data. And so what I'm going to do is I'm going to take my comment menu, and I'm going to write some things down here. So for example, I'm going to say position 1 was right exactly when he let go of it. So that would be 0 seconds. And I can see that it has not fallen at all. It is right there on the 0 mark. So position 1 is also 0 meters. And put M for meters, okay? Position 2. All right, now this is where we get this nasty number that they gave us to work with right here. How long has the ball been falling now? It has been falling for 0.087 seconds at position 2, which is how many meters? I have to look. Let me see, that's 1 meter. Every little line would then be 0.1. Oh, look, it's even, number 2 is, it hasn't even reached the first line yet. So it's less than 0.1 meters. What do you think? Is it halfway to the 0.1 mark? Or is it not quite there? Personally, I think it's not quite there. So it's not 0.1. Half of 0.1 would be 0.05. So I think it might be 0.0, just a little bit less than 0.05 meters. Well, it looks like I misspelled position over here. Postition, okay. I'm making up new words as I go. Position or image 3. Oops, I misspelled it again. Position, again. If at first you don't succeed, then do it over, do it right. So position 3 now, it's fallen for another 0.087 seconds. I'm going to punch into my calculator 0.087 plus 0.087, and that's going to give me 0.174. 0.174 seconds have now gone by. And how far has it fallen? Position 3. Oh, it fell past the first mark. It's not quite to the second mark, though, is it? So it's going to be 0.1. I'm looking right where the line goes across the middle of it. That's where I'm measuring from. And I think this line is about at the halfway mark. So I'm going to call that 0.15 meters. I'm going to do one more, maybe two more for you, and then you're going to do the rest. Position 4 equals, let me see. I got to go 0.174, which I already had, and I just left it on my calculator. And I'm going to add another 0.087 to 0.174, and that gives me 0.261 seconds. And when I look at position 4, where am I now? I'm past mark number 1, past mark number 2, just barely past mark number 3. And I'm going to use, again, this red line across the middle of position 4. And so to me, that looks like it's not halfway between the third and the fourth mark. It's not halfway between those. So it's less than halfway, so it's less than 0.5. I'm going to call it 0.2. 0.32 meters. How did I get 3.2? I'll show you one more time. So first of all, it's 0 point something because we haven't crossed the 1 meter mark, have we? Nope. Secondly, it's 0.123 meters, but it's a little more than that. So it's 0.32 meters. I keep doing this until I end up down at position 10. I'm going to let you fill in all those blanks. I'll look at position 10 with you. Position 10 equals, well, you would think it would be 0.087 times 10, except remember that position 1 didn't count. So it's really 0.087 less than that. So that's what you should end up with, is 0.783, 0.783 seconds that it took to fall that far. That's still less than 1 second, isn't it? 0.7, a little more than half a second. And I can see from looking at the red cross on the ball that it's exactly at 3 meters, 3.0 meters. That's how you're going to do this part. I want you to fill in the gaps between position 4 and position 10. All right? That's the data that we're going to work with. We have the time. We have the distance that it fell. Oh, and we have the location too. So you fill in the rest of that for yourself. Okay, next thing. When we organize data, it's supposed to go in a specific order. First, what objects we are studying. Stop. What object are we studying here? That's going to be number 1. What object are we studying? Oh, well, it looks like we're just studying a ball, right? What about the next thing? First, what objects we're studying, then the independent variable, what we modify, what causes changes. Well, that to me looks like it's the time. But wait a minute, there's also position in there, huh? Maybe that should be number 2, is the position it's in. In fact, I think it would be better if we called this the ball position. Then we have the amount of time that has gone by. That's causing this to change. The amount of time causes it to fall farther. As the time goes by, it keeps falling more and more. Next, we have the dependent variable, which is what we measure. What did we measure? Didn't we measure the distance it fell? So wouldn't that be number 3? Finally, what we calculate after collecting the data. Now remember, whenever it says calculate, we have to do math. Or should I say, we get to do math. Woohoo! At any rate, let's go back up here. What are we trying to find out? We want to study how fast the ball is falling, right? And that means we have to find its speed. That's what we're going to calculate for number 4 down here, is speed. Are you with me on that? Then please notice it says that we also want to do this and to add them to our list. I'm going to let you do that for yourself. I'm not going to do this whole thing for you. I'll get you started, but you got to do some of this yourself. All right? Okay, moving on. Now we're going to do a data table. We're going to take our data and analyze it. Okay, so here they called this image. I would rather call it position. And that should be really easy. 1, 2, 3, on down the line, right? I can't quite line that up correctly. Maybe I needed to do that a little differently. If I changed the size of my font, it might have worked perfectly though. Next, they've given us a hint here. They've said this one should be time. And they've also given us another hint that we should first write down the abbreviation we're using, which is T. Second, we should write down what it stands for, time. And third, we should write down how we're measuring it. So this one we're measuring in seconds. So at position 1, as I recall, it was 0 seconds, wasn't it? Because it was just before we dropped it, or at the very moment that we let go. And then every time after that, we just add 0.087 to whatever we did before. So position 1 was 0 seconds. Position 2, 0.087 seconds. Now I'm going to take this number and add the same number to itself, 0.087, and that's going to give me 0.174. In position 4, I'm going to add the same number again. I just keep every time on this chart, you're going to add 0.087 to whatever number you left off at. So for this one, 0.087 plus 174, didn't I do this math already? Yeah, there it is. It's 0.261. So 0.261 goes there. And you're going to keep going, of course, all the way down to 10. Keep going all the way down, fill in all those times. You might as well just do it right now because you put this number in your calculator, 0.261, add 0.087 to it, write that down. Add 0.087 to it again, write that down for the next one. Add 0.087 to whatever that was. Every time you just keep adding 0.087. And then the very last one, if you do it right, should end up being right here, 0.783. Okay, next thing we're going to do, it didn't give us this hint, but I'm going to give it to you. What else did we notice? What else did we pay attention to? We watched distance, right? So I'm going to put D, which stands for distance, And I'm going to put in parentheses that I measured this in meters. And as I recall, because number 1 was at the very moment the guy let go, it hadn't fallen at all yet. So that one's just 0 meters for number 1. Simple. For position 2, I'd already measured it. All I have to do is take these numbers that I'd already figured out and move them onto the chart. 0.04 is the next one. Again, I want to be as accurate as possible. That's why I went all the way down to 0.04 instead of just calling it, 0.05 or 0.1 or something. I wanted to be accurate. Also notice that here, every time I wrote down seconds, every time I wrote down meters, and now I'm taking a shortcut, and instead of doing that, I put the measurement up at the top. If I've got the measure up here, I don't have to write it down here. So this one was 0.15. What was my next measurement? 0.32 meters. That was position 4, huh? Right there. I think I used a comma. There we go. 0.32 meters. All right. There it is. You're going to fill this all the way in, right? All the way down to position number 10. Do that for yourself. This is easy. Just number 5, 6, 7, 8, 9, 10. This one, whatever number you have, add 0.087 to it again. This one you have to measure for yourself off of this picture, which hopefully you already did back on this question. Next, they've given us a hint up here at the top that they want us to calculate V. Well, what is V? What do you think V stands for? I'll bet you know that it's velocity, huh? Kind of like speed, but it also includes direction. So most of the time, speed and velocity in our daily lives are treated the same. But in physics, velocity means that you're going a certain direction. It's like, oh, I'm going one direction down the hall, you're going the opposite direction down the hall. We have the same speed, but we have different velocities if we're not going the same direction. And the way we measure velocity is really the same we measure speed. It's measured in this case, meters per second. Meters per second, which would be just like miles per hour, except these are meters instead of miles, much smaller, and seconds instead of hours, also much smaller. Notice they've given us up here an equation to use. To calculate velocity, we go 2 times d divided by t. What's d? Oh, distance. What's t? Ah, there it is, it's time. So this first one's easy. What's 2 times 0? That would be 0. Divided by 0 would give a velocity of, wow, 0. Doesn't that make sense? We've just now released the ball in this very moment, and it hasn't started falling yet, so it has no velocity. It's not moving. Okay, this next one is trickier. In fact, I'm going to do this, well, I don't know if you'll be able to see it or not. On the calculator, I'm going to go ahead and pull up my calculator on my screen here. I don't know if you'll be able to see it, and it'd be really cool if you could. But let's find out, or you can let me know if it worked or not. So I'm going to take my calculator out of the way. I want to remember that my numbers are V equals 2D over T. Where's D? There it is, 0.04. So I'm going to start with 0.04 times 2, and then I'm going to hit the equals button. And then I have to divide by t. Divided by, let's see, which one was this one? This one, 0.087. 0.087. Make sure you get those decimal points. Sometimes when you click on them, they don't show up. I can see that it did for mine. My answer, my velocity is 0.91954022988505575 meters per second, but I'm just going to round this off to the hundredth place. Tenths, hundredths, a 9. I'm going to round that up to 0.92. So there we are, 0.92 meters per second. Well, I already wrote that down, so I don't have to write it again. Let's do the next one. I'm going to hit the clear button. 2d over t. D was 0.174. I could put the 2 in first, that'd be okay. But I'm going to put the 0.174 in just to make sure I got the right number. I'm going to multiply it by 2. I hit the equals sign before I move on. Then I divide by the distance. Uh-oh. I hate it when I do this, don't you? I did everything backwards. I have to go back and do the first one over again. I did it wrong. Darn. Well, oh well. What do you do? If you make a mistake, you figure it out. Actually, I did the first one right, didn't I? Did I go 0.04 times 2 divided by 0.087? Did I do that? I think I did do that one right. Yeah, I did. So the first one's fine. Good. Second one is where I was messing up. 2d. So I have to start with 0.15. Yeah. Be very careful. You got to put the correct thing in first. It's got to be d. 2 times d, the distance, 0.15 times 2, hit the equal sign, divided by the time, 0.174. And that gives me an answer of 1.724. Now I'm going to round it off to this one. 2 numbers after the decimal point. I look at the number behind it. Oh, if it's 5 or less, I add 1 to this. Excuse me, 5 or more, I add 1 to this. If it's 4 or less, I leave it alone. So in this case, I'm going to leave it alone. 1.72 is my velocity. Last one I'm going to do with you. Clear everything. What was it? 2d. This is d, so that's the right one. 0.32 times 2. 2d, right? Distance times 2 equals, make sure you hit that equal sign between. It's going to just make sure you're doing it right. Divided by my time, divided by t. This one was 0.261. Hit the equal sign. Boom, I got my new answer, 2.45. And the number after the 45 is a 2. That's not big enough to raise this up, so I leave it as 2.45. 2.45 meters per second. Wow, let's just look at this data for a minute. What's happening? The velocity went from 0 to 0.92 to 1 point. It looks like the velocity is getting bigger, doesn't it? Does that mean the ball is falling faster and faster? Or does it fall at a constant speed? Sure looks like it's falling faster and faster. Well, I'm going to stop here, and you're going to keep going all the way to number 10, but I want you to keep that question in the back of your head. Is it getting faster as it's falling? In other words, is it accelerating? Speaking of acceleration, look at this. They've got another space for us to fill in here. A. I better put the label on there first. A must be acceleration, right? And we're going to measure this. It's not something I really am too concerned about you understanding. It's meters per second, which is velocity per second. We call it meters per second squared. Or another way to think about it is velocity per second, the change in velocity over time. But usually we would not call it velocity per second. We would call it meters per second squared. Oops. Meters per second squared. Not times 2, times itself. Again, that's a detail we don't really need to worry about. And now this is a little bit more complex of an equation. 1/2 v squared divided by d. Fortunately, when we start, we're going to go v squared. For the first one is 0 times 0 is still 0, times 1/2 is still 0, divided by the distance of 0 gives us an amazing acceleration of 0. We haven't let go of the ball yet. It hasn't had a chance to accelerate. Position 2. Let's jump back to our calculator. I hope you can see the calculator. All right. What do I have to do? 1/2 v squared divided by d. The best way to do this is to start by getting your v. So the v was 0.92. 0.92. And then you want to find your x squared button. If you're using the calculator on your phone, if you turn it sideways, it will give you a whole bunch of new buttons. Turn your phone sideways and you'll find the x squared button if you didn't have it before. Boom, there it is. That's 0.92 squared. That's v squared. 1/2. Well, there's a couple ways of dealing with this. We could divide by 2. After all, it shows it over 2. Or we could multiply by 0.5. Either way works. Multiply by 1/2 is the same as dividing by 2, whatever makes the most sense to you. The equation actually says 1/2 times v squared, doesn't it? So I'm going to go ahead and go times 0.5. Once again, I should hit the equals button. Okay? So that's 1/2 of v squared. I'm going to start all over again because that number looked weird to me. I just want to double check my work. It's never wrong to double check your work. It's a pretty wise choice. There's v, 0.92 was from over here. Now I'm going to square that. Now I'm going to multiply it by 1/2, or I'm going to divide by 2. Either way, okay, I'm happy. That's the same number it was before. That was the 1/2 v squared. The last thing I have to do is divide by d. So divide by, what was my d? Make sure I got the right one. 0.04. 0.04. Hit the equals button. My acceleration, 10.58. And that, again, is measured in meters per second, or meters per second squared, or velocity per second, or change in velocity is what we're really talking about here. How much is the velocity changing? That's what we mean by acceleration. All right, let's do the next one. What was v? 1.72, it looks like. Yep. 1.72 squared, and then times 1/2. Easiest way is to just divide by 2. Equals, make sure you hit that equal sign every now and then. And then my last thing is divided by d, and this time d was 0.15. Divided by 0.15 equals 9.86. 9.861. That's too small to raise up the 6, isn't it? So there we go. 9.86. Next one. Clear everything out of the way. By the way, this actually means clear everything. This means only clear the most recent entry. Clear entry is what this is. So that would not clear everything. This one clears it all. So what do I need to do again? I need to find velocity right there, 2.45. I need to square it. I need to divide it by 2 or multiply by 1/2. They are the same thing. Hit the equal sign. Then I have to divide by d. D was 0.32. Divided by make sure you get those decimals in there. 0.32 equals 9.378. Okay, I want to keep the first 2. Then it's an 8. That's big enough that I should round that up to be 9.38, don't you think? 9.38. Cool. That is how you're going to fill in the rest of this data table for yourself. All right. Then when you finish that, I would like you to answer these 4 questions. Actually, there's not 4 questions. There's statement number 1, time increases with each image. We're talking about the photo of the ball. Each image, number 1, 2, 3, 4, 5, 6, 7, or each position, more time has gone by, right? Because in our world, time always moves forward. So time increases with each image. It never goes backwards. What would it mean if time went sideways? At any rate, time increases with each image. We know that's true. Now, this is what you're going to do for yourself. As time increases, distance, and then you're going to circle which one of these you think would be the best. Again, you can use your circle tool up here to make a circle, right? And then you can drag it to where you want it to be. I think it's easiest to drag it if you click away from it and then come back to it, right? Circle decreases, circle stays the same, circle increases, whichever one you think is true. Then you can do the same thing with distance. I'm going to change the size of this circle, and then does distance increase uniformly? Remember, if it's uniform, it's the same amount. Just like in a military uniform, everyone is wearing the same thing. Or if we had school uniforms, we'd all be dressed the same. They want to know, does distance increase uniformly? Does the amount of distance get bigger and bigger by the same amount every time? Or does it vary? Then you have to justify your answer. In other words, give evidence to your answer that it either did or did not increase uniformly. As we go down here, number 3, now they're not giving you the blanks to fill in, but basically these are still your 3 choices. As time increases, velocity, did it get faster, did it get slower, or did it stay the same? Does velocity increase, decrease, or stay the same? Was it a uniform increase? Was it always changing by the same amount every time, or not? Please justify your answer. And then what about acceleration? Did it increase, decrease, or stay the same? I will give you a hint on acceleration that you want to make sure when you're saying that something increased or decreased, that it's a very strong and obvious pattern. If it's just kind of jumping around the same number, it's not always exactly the same number, but it's similar numbers all the time, then we would not count that as an increase. That would probably just be a little error in measurement that gave us a slightly incorrect number. So right here, I'm seeing a very clear increase in velocity, definitely getting bigger and bigger, faster and faster. Over here, what I'm seeing in acceleration, I kind of have to ignore the 0. It almost seems like it's getting slower, but I want you to look for a pattern. Will this pattern continue? If it's truly getting slower, by the time you get down to the end, it would be like, I don't know, way less than 9.3, huh? On the other hand, maybe this is just some random measurement error, and it isn't really changing. So be careful on that one. That takes care of page 4. And then we're going to get into the graphing part another day, all right? So if you get this stuff done by Monday, you're going to be in great shape. Okay, and I think I'm going to call it a day for you. And here I am floating in the universe, as we all are on planet Earth, floating through space, huh? So I hope you have a good time. I hope that helped. Let me know if you need more hints. All right, see you later.